Welcome back to the show. I'm Nadia, and today we're doing something a little different, a deep, patient walk through the physics behind a project called QuantSim. The one-line version is simulating a black hole horizon on a chip. And with me to actually make that make sense is Sam. Sam, thanks for doing this.
Happy to be here, Nadia. And I want to set expectations up front. This isn't going to be a gee-whiz black holes episode. We're going to build the real thing, brick by brick. What Hawking radiation actually is, how you smuggle a curved spacetime onto a chain of atoms, how you shake that chain to control it, and then the part everyone's excited about, which is what happens to information when it falls in. By the end, you should be able to sit across from a author and hold your own on every piece of it.
That's the goal. So let's not rush. Start me at the very beginning. Black holes. Why does anyone think a black hole has a temperature at all? Isn't a black hole, by definition, the thing that nothing escapes?
That's exactly the paradox, and it's a good place to start because the tension is the whole story. Classically, meaning Einstein's general relativity, no quantum mechanics, a black hole is perfectly black. It has an event horizon, a one-way membrane. Cross it going in, and you can never send anything back out. Not light, not a signal, nothing. So classically, its temperature is exactly absolute zero. It just sits there.
Right, the Cosmic Roach Motel.
Exactly. And that was the picture until the early 1970s, when a few people started poking at it. Jacob Bekenstein noticed something strange. If you throw a hot cup of coffee into a black hole, the entropy of the universe outside just dropped. The disorder you carried in vanished behind the horizon, and that seems to violate the second law of thermodynamics, which says total entropy never decreases. Bekenstein's fix was radical. He said the black hole itself must carry entropy, and that entropy is proportional to the area of its horizon. Not its volume, its area. So the coffee's entropy isn't destroyed, it's added to the horizon's ledger.
Okay, but entropy and temperature come as a package in thermodynamics. If it has entropy, it has to have a temperature.
You just did the physics. That's precisely the corner Bekenstein backed everyone into. If a black hole has entropy, thermodynamics demands it also has a temperature. And if it has a temperature, then it has to radiate, like any warm body. But radiating means emitting something, which a classical black hole absolutely cannot do. So there was a genuine contradiction sitting in the field, and it took quantum mechanics to resolve it.
Enter Hawking.
Enter Stephen Hawking, 1974, 1975. Hawking did the honest calculation. He took a quantum field, think of it as the electromagnetic field, or any field that can have particles, and he studied it not in flat, empty space, but on the curved background of a black hole. And he found that the vacuum near the horizon is not empty. It emits a steady thermal stream of particles. The black hole glows.
Let me slow you down there, because the vacuum is not empty is one of those phrases people say and nod at without understanding. What's actually happening?
Good, let's make it concrete. In quantum field theory, the vacuum, truly empty space, is not still. It's a boiling sea of fluctuations. Pairs of particles, a particle and its antiparticle, are constantly flickering into existence and annihilating back to nothing. So fast you can never catch them. We call them virtual pairs. In ordinary flat space, they always recombine and pay back the energy they borrowed. No net particles, ever.
But near a horizon.
Near a horizon, geometry gets to intervene. Imagine one of those pairs pops into existence, straddling the event horizon. One partner just outside, one just inside. The inside partner falls in and is lost. The outside partner has nothing to recombine with, so it becomes real. It escapes to infinity as an actual particle. From far away, you see a stream of these escapees. That's the radiation. And here's the accounting that makes it beautiful and a little eerie. The infalling partner carries negative energy, as measured from outside. So when it's swallowed, the black hole's mass goes down. The hole is literally paying for the radiation out of its own mass. It evaporates.
So the radiation isn't coming from inside the black hole, which would be forbidden. It's coming from the horizon itself.
That is the single most important thing to hold on to for this entire episode, so I'm going to say it slowly. The Hawking radiation is a property of the horizon, not the interior. Everything is decided right at that surface by the local geometry there. Nothing has to reach in and pull information out of the deep interior. Keep that locality in your pocket, the whole lab simulation scheme will get to lives and dies on it.
You keep saying thermal. How hot is it? Is there a formula?
There is, and it's one of the most celebrated formulas in physics because it ties together four completely different domains. For a simple, non-rotating, uncharged black hole, a Schwarzschild black hole, the Hawking temperature is Th equals h bar times c cubed divided by 8 pi times g times kb times m. Let me unpack that symbol soup because every letter is a different pillar of physics in one line.
Please, one at a time.
H bar is Planck's constant, that's quantum mechanics. C is the speed of light, that's special relativity. G is Newton's gravitational constant, that's gravity, general relativity. Kb is Boltzmann's constant, that's thermodynamics and statistical mechanics. And m is the mass of the black hole. So this one little equation has quantum mechanics, relativity, gravity and thermodynamics all shaking hands. That almost never happens. When four pillars meet in one formula, physicists pay very close attention, because it usually means there's a deeper theory underneath that we haven't fully seen.
And notice the M is on the bottom.
You caught the punchline. The mass is in the denominator, so the temperature is inversely proportional to the mass. Big black holes are cold, small black holes are hot. A black hole the mass of our Sun has a Hawking temperature of about 10 to the minus 8 Kelvin. That's 1/100th of a millionth of a degree above absolute zero. That is unimaginably colder than the cosmic microwave background, the leftover glow of the Big Bang, which bathes everything at about 2.7 Kelvin. So a real astrophysical black hole is actually absorbing far more than it emits. We are never ever going to measure Hawking radiation from a real black hole directly. It's hopeless.
Which is presumably why we're building fakes. But before we get to fakes, there's a cleaner way to write that temperature, isn't there? One that doesn't care about the mass or Newton's G at all.
Yes, and this is the form that matters for everything downstream, so let's dwell on it. You can rewrite the Hawking temperature as Kb times Th equals h bar times kappa, divided by 2 pi times c. Here kappa, and I'll call it the surface gravity to avoid confusion with a hopping amplitude, we'll meet later. Kappa is the strength of the gravitational field right at the horizon. Roughly how hard the horizon pulls, or equivalently how steeply the geometry is changing as you cross it.
So the temperature is just proportional to the surface gravity.
Just proportional to the surface gravity. Linear. And that's profound because look what dropped out. The mass is gone, Newton's G is gone. The temperature is set entirely by the local steepness of the geometry at the horizon. That's the locality principle again, now in equation form. The horizon doesn't need to know how big the black hole is or what fell in a billion years ago. It just needs to know how sharply space-time is bending right there, right now. Steeper bend, hotter hole.
And I have a feeling steepness of the geometry at the horizon is going to become steepness of some knob in a lab.
You're getting ahead of me, and you're exactly right. Hold that thought. But first, the conceptual leap that makes the lab version legal at all. And it goes back to 1981, to a physicist named Bill Unruh.
This is the sonic black hole idea.
This is the sonic black hole, the dumb hole. Dumb as in mute, silent, not stupid. Unruh was teaching fluid mechanics, and he noticed a gorgeous analogy. Picture a river flowing toward a waterfall. It starts slow and speeds up as it approaches the edge. Now imagine fish in that river who can only communicate by sound. The fastest signal in their world is the speed of sound in water. Upstream, where the river flows slower than sound, a fish can always shout back upstream. Its voice makes headway against the current.
But somewhere the river gets faster than the fish's shout.
Somewhere the flow speed equals the speed of sound. And past that line, the water is moving downstream faster than any sound can travel upstream. A fish beyond that point can scream with all its might and the sound still gets swept over the falls. It can never send a signal back. That line, where flow speed equals sound speed, is a horizon. An acoustic event horizon. It traps sound exactly the way a black hole traps light.
And this is a real horizon, not just a poetic one.
That's Unruh's deep point. When he worked out the mathematics of sound waves, phonons, riding on that flowing fluid, the equation he got was identical, term for term, to the equation for a quantum field on the curved spacetime of a black hole. Not similar. Identical. Same mathematics. And mathematics doesn't know whether it's describing curved spacetime or flowing water. So if the equations are the same, the physics is the same, which means that sonic horizon should emit thermal Hawking radiation too, made of phonons, at a temperature set by how steeply the flow speeds up as it crosses the sound barrier.
So Unruh basically said, you don't need gravity to have a horizon. You need a flow and a maximum signal speed.
That's the whole liberation. Horizon physics is not about gravity specifically. It's about any medium where a background flow overtakes the local signal speed. Gravity is just one example. And once you realize that, a door swings open. Build a laboratory system whose governing equation matches a quantum field on a curved background, and you can study horizon physics on a benchtop. That's an entire field now. It's called analog gravity. People have done it with flowing water tanks, with light in moving media, and most spectacularly with Bose-Einstein condensates. Jeff Steinhauer in Israel actually measured a thermal spectrum of phonons from a sonic horizon in a condensate. He saw analog Hawking radiation.
So why don't we just stop there? If the condensate experiments already saw it, what's left to do?
Beautiful question. And the answer is the reason this whole project exists. Seeing the radiation is step one, and it's been done. But the deep questions about black holes aren't about the radiation being there. They're about information. What happens to the quantum information of something that falls in? Does it come back out in the radiation, scrambled beyond recognition, or is it lost forever? That's the black hole information paradox, and it's arguably the sharpest unsolved problem at the border of quantum mechanics and gravity. And to study that, you need interactions, particles that talk to each other, that can scramble information among themselves. A flowing fluid gives you the horizon, but the interacting, information-scrambling version is exactly where the fluid analogues and classical computers both hit a wall. That wall is why you reach for a quantum computer. But we're getting ahead again. Let's build the horizon first.
Okay, so this is the heart of the project, the part where a curved spacetime turns into a chain of atoms. Walk me in slowly. What is the physical system?
The system is about as simple as quantum physics gets. It's a one-dimensional chain of sites. Think of a row of little wells or a row of atoms and a single quantum particle that can hop from one site to its neighbor. Physicists call it a tight binding chain. You write down its energy, its Hamiltonian, as a sum over links. For each link between neighboring sites I and j, there's a term that lets the particle hop, and it's weighted by a number, kappa ij, the hopping amplitude, times an overall energy scale we'll call J0.
So kappa here is not the surface gravity from before, it's the hopping strength. Different kappa.
Different kappa, and I apologize on behalf of all of physics for reusing the letter. From here on, when I say kappa, I mean the hopping amplitude, how easily the particle tunnels across a given link. If kappa is big, the particle moves freely across that link. If kappa is small, the link is sluggish. If kappa is 0, the link is cut. Now, in an ordinary crystal, every link is identical. All the kappas are equal. And when you solve that, you get the textbook result. The particle's energy as a function of its momentum, EQ, is a cosine. Energy equals -2 J0 kappa, times the cosine of Q times D, where D is the spacing between sites.
A cosine band. Okay, why do we care about the shape of that curve?
Because of what happens when you fill the chain halfway, half filling, band center, and zoom in on the particles near that point. Right at the middle of the cosine, the curve is passing through steeply and crucially, almost straight. If you expand the cosine around momentum Q equals pi over 2d, the energy stops looking like a cosine and starts looking like a straight line. Energy is approximately plus or minus v times the little momentum, where v is a velocity equal to 2 J0 kappa d.
And a straight line relationship between energy and momentum means
You've got a massless relativistic particle. This is the key move, so let me make it vivid. For a slow, ordinary particle, a marble, energy goes like momentum squared, a parabola. For a massless relativistic particle, a photon, light itself, energy is exactly proportional to momentum, a straight line, with the slope being the speed of light. So when the low-energy excitations of this humble atomic chain have a straight-line energy-momentum relation, they are behaving mathematically like massless relativistic particles, like little bits of light, and their speed of light isn't 3 times 10 to the 8 meters per second. It's this v, 2j0 kappa d, an effective speed of light that you, the experimentalist, get to set.
So already the chain is pretending to be a relativistic world with its own speed of light, but it's a flat world so far. Where does curvature come in?
Here's the move that makes the whole project sing. What if the hopping isn't uniform? What if kappa changes as you go along the chain? Strong hops here, weak hops there. Then the effective speed of light, v, which was 2j0 kappa d, becomes position-dependent. The local speed of light is different in different places along the chain.
And a position-dependent speed of light is
Precisely what a curved spacetime does. That is what gravity is, in a very real sense. Near a massive object, clocks run slow, and the effective speed of light, as seen from far away, changes with position. A varying local light speed is the signature of a curved metric. So if you make the hopping amplitude vary along your chain in just the right pattern, the massless particles living on that chain feel like they're moving through a curved spacetime. When you do the careful continuum limit, and the cold atom proposal does this rigorously, using objects called vierbanes that translate between the lattice and the geometry, you find the chain's low-energy physics is exactly the massless Dirac equation for a relativistic particle in a curved 1 plus 1-dimensional spacetime. One dimension of space, one of time.
I want the dictionary, the literal translation rule. If someone hands me a curved spacetime, a metric, a shape, how do I know what hopping pattern to program?
And this is the sentence you want to be able to say in one breath to your co-author. The rule is, the hopping amplitude on each link is just the curvature function sampled at that location. Concretely, the metric is captured by a function f of position, and the hopping on the link between site j and site j plus 1 is f evaluated at site j plus f evaluated at site j plus 1, all divided by 8 times the spacing d. That's it. Each link just reads off the value of the geometry function f at its own location and sets its hopping accordingly. Choose your units so that h bar times c equals j0, and the correspondence is exact. Geometry has become a hopping pattern. The shape of spacetime is now literally a list of tunneling strengths you dial into a lattice.
That's genuinely elegant. So now, the horizon. In the real black hole, the horizon was where the effective velocity did what?
Where the effective velocity, the local speed of light for these particles, goes to 0. Remember, v is proportional to kappa, the hopping. So the horizon on the lattice is the place where the hopping amplitude passes through 0. And here's the gorgeous part. To build a black hole with an interior, you need the geometry function f to change sign as you cross the horizon. Positive outside, negative inside. And since the hopping just samples f, the hopping changes sign too. The hops are positive on one side of the horizon and negative on the other.
A negative hopping amplitude. What does that even mean physically? Negative tunneling.
It means the hop comes with an extra minus sign, a phase of pi, on the particle's wave function when it crosses. It's a perfectly legitimate quantum amplitude. Amplitudes are allowed to be negative or even complex. But physically, that sign flip is the lattice fingerprint of the black hole interior. It's how the chain encodes, you are now inside. And right at the horizon site, where the hopping passes through 0, the effective speed of light is 0. The light cones, the little cones that say how far a signal can reach, close up completely. They pinch shut. A classical particle sitting there simply freezes. It cannot move because its maximum speed is 0.
So nothing crosses.
Nothing classical crosses. But and this is one of those moments where the analogy pays off almost too well, a quantum particle can still get across by tunneling. Quantum mechanics lets a particle sneak through a region it's classically forbidden to enter. And in the real black hole story, there's a picture of Hawking radiation, due to Parikh and Wilczek, that describes the radiation as literally quantum tunneling across the horizon. So on the lattice, the only way across the frozen horizon is quantum tunneling, which is the exact same mechanism that produces Hawking radiation in that picture. The analogy isn't loose. It reproduces the mechanism.
I love that. Okay, and the temperature? We had that beautiful temperature equals surface gravity formula. What's the lattice version?
Let's derive its shape in words. Take the simplest horizon, a straight ramp. Let the hopping increase linearly as you move along the chain, passing through zero right at the horizon site. So the hopping on link J is some slope, call it alpha, times how far site J is from the horizon. Positive on one side, zero at the horizon. Negative on the other, a clean straight line through zero. That slope alpha is the lattice's version of surface gravity. It's literally how steeply the geometry changes at the horizon, which is exactly what surface gravity measured in the real black hole.
And the Hawking temperature was proportional to surface gravity.
So it's proportional to alpha. When you carry the surface gravity formula through the continuum to lattice translation, in natural units where h bar, kb, c, j naught and the spacing are all set to 1, everything collapses to a formula you should tattoo somewhere. Th equals alpha over 4 pi. The Hawking temperature of your simulated black hole is the slope of the hopping ramp, divided by 4 pi. One number, the steepness of how fast the tunneling changes across the horizon, sets the temperature. Make the ramp steeper, the hole is hotter. It's a knob. You turn a dial in the lab, and you've set the temperature of a black hole.
That is the sentence, isn't it? The temperature of the black hole is the slope of the hopping ramp over 4 pi.
That's the sentence. And I want to flag something honest here, because it comes up in our own numerical work. There are two ways to measure that temperature in a simulation, and they're worth distinguishing. One way is spectroscopic. You look at the energy spectrum of the emitted particles and fit a thermal, blackbody-like distribution to it, and read off the temperature. The other way is dynamical. You literally watch a particle at the horizon, track where its density piles up over time, and extract the temperature from the timing of that peak. In our own reproductions, the dynamical density peak method is the clean, calibrated one. We got the temperature proportional to 1 over the peak time with essentially perfect fit quality. An R² of 1.00000. The spectroscopic method is proportional to the right answer, but comes out about 1.8 times high because of finite size and fit window artifacts.
And you didn't fix that 1.8?
We did not, and I want to be emphatic about that, because it's a matter of scientific integrity that runs through the whole project. That factor is a real artifact of a small, finite system and the window you fit over. It is not a mistake to be quietly corrected, and it is absolutely not something to fudge, so the number lands where you wish. We report it exactly as it comes out, 1.8 and all, and we say in plain language why it's there. Blind analysis. You never reach in after the fact and multiply by a correction to hit the answer you expected. If a control disagrees, you diagnose it. You don't massage it.
Good. That honesty is going to matter when the co-author pushes. All right, we've turned geometry into a hopping pattern, and we've got positive and negative hops. But here's my naive question. In a real lab, how on earth do you make a negative tunneling amplitude? You can make atoms hop, sure, but you can't exactly tell them hop with a minus sign.
And that is the perfect segue into the third pillar, which is the experimental magic that makes all of this buildable. It's called Floquet engineering. And the one-sentence version is, you can completely reprogram how a quantum system hops by shaking it, periodically, very fast.
Shaking it? Like physically wobbling the whole apparatus?
Sometimes literally that, physically oscillating the optical lattice back and forth. Or equivalently, wobbling the energy of individual sites up and down in time with a periodic drive. The general principle is named after Gaston Floquet, a mathematician who studied differential equations with periodic coefficients back in the 1880s. The physics version says, if you drive a quantum system with a periodic force that's fast compared to its natural dynamics, then on average, over each drive cycle, the system behaves like a different, effective static system. And crucially, the effective system can have properties the original one never had. You can conjure up new physics just by shaking.
This feels like it should be too good to be true. Give me the mechanism. Why does shaking change the hopping?
Let's do it properly, because the mechanism is a lovely piece of mathematics, and it's directly the technique in one of our core papers. Picture two neighboring sites, and we wobble their energies up and down in time. A periodic drive of amplitude A and frequency omega. Now go into the reference frame that rides along with that wobble. Physicists call it the rotating frame or the interaction picture. In that co-moving frame, the drive gets absorbed into the hopping term, and the hopping picks up a time-dependent phase. Specifically, the hopping amplitude gets multiplied by a factor that looks like e to the I, times some amplitude times the sine of omega t, an oscillating exponential phase.
A complex exponential of a sin. That's the kind of thing that looks intimidating but usually has a trick.
It has a beautiful classic trick, and it's the heart of the derivation. It's called the Jacobi-Anger expansion. It says that e to the iz sine theta, that exact intimidating object, can be rewritten as an infinite sum of nice clean pieces, a sum over all integers n of jn of z times e to the in theta. The jn here are the Bessel functions, special functions that show up whenever you have waves with circular or cylindrical symmetry, like the vibrations of a drumhead or ripples on a pond. So the Jacobi-Anger expansion takes your ugly oscillating phase and decomposes it into a ladder of Bessel function harmonics.
And why does that help?
Because Floquet engineering cares about the time average, the effective static system you get after averaging over the fast drive cycles. When you average that Jacobi-Anger sum over a full period, every term with an not equal to 0 oscillates and averages away to nothing. Only the n equals 0 term survives, the piece with no time dependence. And that surviving piece is J0 of z, the zeroth Bessel function, evaluated at the drive amplitude. So the upshot is stunningly clean. The effective hopping is the bare hopping, multiplied by J0 of the drive amplitude over the frequency. Shaking renormalizes your hopping by a Bessel function.
So the drive amplitude is a dial, and turning it multiplies my hopping by J0 of that dial setting.
Exactly. And now watch why this solves your negative hopping problem. Because it's the punchline. The zeroth Bessel function, J0, starts at 1 when the drive is off. No shaking, hopping unchanged, makes sense. As you crank up the drive amplitude, J0 decreases, dips down, and then, here's the magic, it crosses 0 at a drive strength of about 2.4 and goes negative. It oscillates, gently damped, between positive and negative values forever after.
So by shaking harder, I can drive the effective hopping down to 0.
Which builds you a horizon where the hopping vanishes.
And if I shake even harder past that crossing, the effective hopping goes negative.
Which builds you the interior where the hopping needs its minus sign. Do you see how perfectly it fits? The two things you needed to construct a black hole on a lattice, a place where the hopping is 0 and a region where it's negative, are handed to you for free by the Bessel function of the drive strength. You don't need exotic materials or negative masses. You just shake different parts of the chain by different carefully chosen amounts, and the Bessel function paints the whole horizon geometry for you. That's Floquet engineering of a black hole.
And this is something the project actually verified numerically?
This is the very first rung of our reproduction ladder, the result we label R01. We took the Floquet driving protocol from the technique paper, I'll name the papers properly in a bit, and we numerically confirmed that the effective hopping really does follow the J0 Bessel curve as you vary the drive, and we matched their figure to better than 0.2%. We also checked the leading correction, because the shaking is infinitely fast assumption is never perfectly true, and the errors from finite drive frequency should shrink as 1 over the frequency squared. We measured that scaling and got a slope of minus 2.00 on a log-log plot. Textbook. That gave us confidence the whole engineering scheme was solid before we built anything fancier on top of it.
One thing nags me. You keep saying fast compared to the natural dynamics. What's the catch? There's always a catch with something this good.
The catch is heating, and it's the honest limitation of the whole approach, so let's name it. When you shake a many-particle quantum system, you're pumping energy in. If the drive is fast enough, the system can't efficiently absorb that energy and it stays in the nice effective state you engineered. That's a regime called pre-thermalization. But no drive is infinitely fast, and over long enough times, the system does start absorbing energy from the shaking, heating up toward a boring, featureless, infinite temperature state, and washing out the delicate physics you were trying to see. So there's a tension. You want to drive fast to suppress heating, but not so fast that other bands of states get involved. Threading that needle, staying in the sweet spot long enough to measure Hawking physics before Floquet heating ruins it, is the central experimental challenge. It's the thing a referee will ask about, and it's the thing the experiments genuinely have to fight.
Good to know where the bodies are buried. Okay, Sam, we've built the horizon, we've learned to shake it into existence. But you said twice now that the really deep stuff is about information. Let's go there. This is the part I find hardest to hold in my head, so go gently. What does it even mean for a black hole to scramble information?
Let's build the intuition before any equations. Imagine you write a secret, a single bit, a 0 or a 1, on a drop of ink, and you let that drop fall into a glass of water. At first, the information is local. It's right there, in that little dark blob. You could scoop it out, but as time passes, the ink diffuses. The molecules carrying your bit spread out, tangle up with all the water molecules, and after a while the information isn't gone. It's still all there, in principle, in the exact positions and velocities of every molecule, but it's utterly delocalized. No local measurement, no scoop of a teaspoon can recover your bit anymore. You'd have to measure essentially the entire glass all at once with perfect precision to get it back.
So scrambling is like that ink diffusing, but for quantum information.
That's exactly it, and the quantum version is even more dramatic. Scrambling means that quantum information initially stored in a few particles gets spread across all the particles, hidden in the delicate web of quantum correlations, entanglement between them. After scrambling, if you look at any small piece of the system, you learn absolutely nothing. The information is only in the correlations of the whole. And black holes are conjectured to be the fastest scramblers that nature allows. You throw something in, and in the shortest time physically possible, its information is smeared across the entire horizon.
Fastest possible. That's a strong claim. How do you even measure the speed of scrambling? What's the ruler?
The ruler is a wonderful object with an awkward name, the out-of-time order correlator, which everyone mercifully shortens to OTOC. Let me build it up. Take two simple operations, two pokes you can do at different places in the system. Call them W and V, sitting far apart at the start. Now do this, poke the system with V, then let it evolve forward in time, then poke it with W, then, and here's the weird part, evolve backward in time, then poke with V again. Because you evolved forward and then backward with pokes interleaved, the time ordering is scrambled. That's the out-of-time order in the name. In a system that doesn't scramble, running forward and then backward should just undo itself. Nothing much happens. But in a scrambling system, that little poke W has, in the meantime, grown to overlap with the faraway V, so the forward and backward evolutions no longer cancel. The OTOC measures exactly that failure to cancel.
So the OTOC is basically asking, has this local poke over here managed to reach all the way over there yet?
That is precisely the physical content. It's the quantum version of the butterfly effect. You measure how a small disturbance in one corner grows to influence a distant, initially unrelated observable. Early on, when W and V are far apart and the poke hasn't spread, the OTOC sits at its initial value. The two operations commute, they don't interfere. As scrambling proceeds, the poke spreads, the operations stop commuting, and the OTOC changes. The relevant combination grows from 0, or a related quantity decays from 1. And in a chaotic, fast scrambling system, that growth is exponential in time. The rate of that exponential growth is called the Lyapunov exponent. Same word as in classical chaos, where nearby trajectories fly apart exponentially.
And now I bet there's a speed limit on that exponent.
There is, and it's one of the most beautiful results of the last decade. The chaos bound, proved by Maldacena, Schenker and Douglas Stanford, in 2016. They showed that for any sensible quantum system at temperature T, The Lyapunov exponent, the rate of scrambling, cannot exceed 2 pi times kb times t divided by h bar. There is a maximum possible speed of chaos, and it's set by the temperature. Hotter systems can scramble faster, but nothing can beat that ceiling.
And let me guess who sits right at the ceiling.
Black holes. Black holes saturate the bound exactly. They scramble at the maximum rate the laws of physics permit. That's the precise quantitative sense in which a black hole is the fastest scrambler in the universe. Not a vague slogan, a saturated inequality. And there's a companion statement about time. The scrambling time, the time for information to fully smear out, grows only logarithmically with the number of degrees of freedom. Logarithmically, that's incredibly fast. Double the size of your black hole and the scrambling time barely ticks up. This is the fast scrambling conjecture. And it's a big reason people believe black holes are telling us something fundamental about how quantum information and space-time fit together.
Okay, but here's my skeptic's question. The OTOC involves running time backward, forward evolution, then backward evolution. You can do that on paper. How could you ever measure it in a real experiment, where you can't just reverse the arrow of time?
Great instinct. And it's the practical crux. You can't reverse time itself, but on a quantum computer or a well-controlled quantum simulator, you can apply the reverse evolution. You apply the inverse of the unitary, the mathematical operation that undoes the forward step. It's demanding but doable. And there's an even cleverer route that sidesteps the whole thing. A route that also happens to be the deepest conceptual link in this episode. It's based on quantum teleportation.
Teleportation as a way to detect scrambling. Now I'm hooked. Connect those.
This is the Landsman experiment, published in Nature in 2019. Verified quantum information scrambling, done on a 7-qubit trapped ion quantum computer. Here's the idea, and it's slick. There's a deep theoretical result that scrambling and teleportation are two faces of the same coin. If you take a quantum system, entangle it with a partner system, then scramble it, then a small amount of information you inject on one side will effectively teleport to appear on the other side. But only if the dynamics genuinely scrambled. If the dynamics were lazy and didn't scramble, the teleportation fails. So you can turn the logic around, try to teleport a qubit through your evolution, and if it arrives faithfully on the far side, that success is a certificate that real scrambling happened. Teleportation becomes a witness for scrambling.
So instead of measuring did the poke spread, you measure did my qubit make it through the wormhole, so to speak.
And that, so to speak, is doing real work. Because in the holographic picture, this teleportation through scrambling is mathematically the same structure as a qubit traversing a wormhole. That's not marketing. It's the same equations. Landsman and colleagues built the protocol on their ion trap, ran it, and used the teleportation fidelity to certify that their engineered dynamics scrambled, and to distinguish genuine scrambling from mere decoherence, from information just leaking away into noise, which is a crucial control because a noisy system can fake some of the signatures.
You said the project engaged with this paper directly. What did we actually do with it?
We reproduced its analysis, and in doing so, we did the kind of careful reading that's the whole point of reproduction. We label this work in our experimental verification lane. We rederived their central protocol equation, their equation 5, and in the process, we found and documented a sign inconsistency in how it was written in the paper, the kind of thing that doesn't change the physics, but that a careful co-author will want flagged. And separately, we verified the fundamental operator identity that the OTOC and the teleportation protocol both rest on, numerically, to a precision of about 7 times 10 to the minus 16, which is machine precision, essentially exact. So we can say honestly that we checked their scrambling teleportation correspondence at the level of the actual operators, not just admired it from a distance.
Let's push the black hole story to its climax. Information falls in, it scrambles at the maximum rate. Does it ever come back out? This is the paradox, right?
This is the paradox, and it has the sharpest possible form thanks to Hawking's own calculation. Hawking's radiation, as he originally computed it, is exactly thermal, featureless, random, like the static hiss of a warm object. It carries no information about what fell in. So if a black hole forms from a book, or from an encyclopedia, or from a star, and then slowly evaporates entirely into this featureless thermal radiation, the information about the book seems to be simply gone, erased from the universe, and that violates one of the most sacred principles of quantum mechanics. Unitarity, the principle that information is never truly destroyed, that in principle you can always run the movie backward. Hawking versus quantum mechanics, that's the fight.
And where does it stand? Is it resolved?
The consensus now, driven by a chain of results, is that information does come back out, subtly encoded in correlations across the entire radiation, not in any single photon. The radiation isn't really featureless, it just looks featureless if you only examine small pieces. Two results anchor this. The first is Hayden and Preskill, 2007. They asked a sharp question. Suppose a black hole is old, meaning it has already radiated away more than half of itself, so it's become highly entangled with all the radiation it emitted earlier. Now you toss in a new qubit of information. How long until that information can be recovered from the outgoing radiation?
And the intuition would be you have to wait for the whole thing to evaporate, which is basically forever.
That's the naive guess, and it's spectacularly wrong. Hayden and Preskill showed that for an old black hole, they call it a mirror in this regime, the information comes back out almost immediately, after just the scrambling time, encoded in a tiny number of extra radiated qubits. The old black hole acts like a mirror that reflects information back out, scrambled but recoverable, essentially as fast as it goes in. It was a stunning result because it said the black hole's interior isn't a permanent vault. For an old hole, it's more like a very fast, very thorough shredder whose output you can, in principle, reassemble.
And the second anchor?
The second is the Page curve, due to Don Page. This is the cleaner, more quantitative statement of what unitarity demands, and it's become the target that any correct theory of evaporation has to hit. Track the entanglement entropy of the radiation. Loosely, how quantum correlated the emitted radiation is with the black hole that's still there, as the hole evaporates. If Hawking were strictly right and information were lost, that entropy would just climb and climb, all the way up, forever, right up until the hole vanished and you were left with a paradoxical pile of radiation more entangled than it has any right to be. But if quantum mechanics holds, if evaporation is unitary, the entropy must rise, reach a peak at the halfway point, called the Page time, and then come back down to zero as the last of the information is returned in the final radiation.
So the Page curve is a rise and then a fall, a tent shape, and the fall is the signature of information coming back.
The fall is everything. A rising then falling Page curve is the fingerprint of unitary evaporation, of information being conserved. A monotonically rising curve is the fingerprint of the paradox, of information lost. And the genuinely exciting development of the last few years is that people have finally derived the falling Page curve from gravity itself using new tools, the quantum extremal surface prescription and these strange contributions to the entropy called islands, regions deep inside the black hole that surprisingly count as part of the radiation's information. It's a very active, very beautiful area, and it's precisely the kind of physics that a scrambling, interacting quantum simulator is built to probe. Because to see a Page curve, to see information turn around and come back, you fundamentally need interactions and entanglement dynamics, not just a single particle bouncing off a horizon.
Which I'm now realizing is the thread running through this whole conversation. The single particle horizon is where you start. The interacting, scrambling, information returning version is where the real prize is. And that's where the classical computer gives up.
You've just written the outline of the last part of the episode. But before we go there, let me put the 3 papers on the table cleanly, since your co-author will refer to them by name and you want to know which is which.
Yes, please give me the map of the 3 papers. Who did what?
3 papers, and it's cleanest to think of them as the blueprint, the tool, and the demonstration. Paper A, I'll call it the cold atom proposal, is Ben Hamu and collaborators on the archive as 2312.14058. This is the blueprint. It's the theoretical proposal that lays out how to build the black hole analog on a cold atom optical lattice. The whole geometry becomes hopping dictionary we spent so long on. The single particle horizon, the prediction of a Hawking spectrum, and the two methods for reading off the temperature. When I talked about the metric to hopping rule and the temperature equals alpha over 4 pi formula, that's the physics of paper A. Most of our reproduction ladder, the results we call R04 through R11, reproduces the figures of this paper. The horizon geometry, the collapsing light cones, the Hawking spectrum, the density peak thermometer.
That's the blueprint. The tool,
Paper B, the Floquet technique paper, is Nixon and collaborators, Archive 2309.12124. This is the tool, it's the how-to for actually engineering those position-dependent, sign-changing hoppings using periodic driving, the Bessel function control we derived with Jacobi anger. It's not specifically about black holes, it's a general toolkit for painting arbitrary hopping patterns onto a lattice by shaking, and it also demonstrates related tricks, building topological edge states and synthesizing artificial magnetic flux for the particles. Our results R01 through R03 reproduce this paper. The Bessel bond control, a topological edge state we pin down to an energy of 9 times 10 to the minus 8, and a tunable synthetic flux. Paper B is what makes paper A physically realizable. The blueprint needs the tool.
and the demonstration, this is the one on real hardware.
Paper C is the one that already happened on a chip, and it's the anchor to reality. It's Shai and collaborators, Archive 2111.11092, and it's a superconducting processor realization. They took a chain of superconducting qubits, engineered the position-dependent couplings to emulate curved space with a horizon, and ran a quantum walk, a single excitation propagating across the engineered geometry, watching it behave exactly as a particle near a horizon should. It's the experimental demonstration that this whole idea works on today's hardware, not just on paper. And this is the paper we engaged with most forensically. We didn't just rerun a simulation, we went back to their actual raw experimental data and reanalyzed it from scratch.
What does reanalyzed from scratch mean concretely? What did you find?
We took their raw data and recovered the actual device Hamiltonian ourselves, by least squares fitting, including the small, unwanted, next nearest neighbor couplings, the stray couplings that a real chip always has and an idealized model ignores. Our reconstruction of their device matched their own simulation to about 5 times 10 to the minus 5, very tight. We then extracted the analog Hawking temperature from their data independently and got about 8.6 times 10 to the minus 5 Kelvin, where their paper quotes 7.7 times 10 to the minus 5. Close, same ballpark, and we can account for the difference. And we noticed and documented a couple of convention subtleties that matter if you're comparing carefully. For instance, that their entanglement entropy is reported in nats, the natural logarithm unit, rather than bits, and a specific sign convention in how they set up the time evolution. Those are exactly the kinds of details that cause two groups to seem to disagree when they actually agree. So we wrote them down explicitly.
That's the forensic reproduction you keep emphasizing. Not we got a similar-looking plot, but we can reconstruct your apparatus from your numbers.
That's the standard we hold to, and it's the standard your co-author will respect. Reproduction means you can regenerate the result from the ground up, and you understand every discrepancy. Not goal-seeking a match, understanding the physics well enough that the match and the mismatches both make sense.
All right. The finale. Why quantum computers at all? We've done an enormous amount with presumably a laptop and some numerical linear algebra. Where's the wall?
The wall is the size of quantum reality itself, and it's worth feeling viscerally. Here's the brutal fact about quantum many-body systems. To describe one particle that can be in, say, 2 states, you need 2 numbers. 2 particles, 4 numbers. 3 particles, 8. Every particle you add doubles the amount of information you need to write down the quantum state, because the particles can be in superpositions of all combinations. So for a chain of L sites, the size of the quantum state, the dimension of its Hilbert space, grows like 2 to the L, exponentially.
And exponentials get away from you fast.
Catastrophically fast. 10 sites, about 1,000 numbers, trivial. 20 sites, about 1 million, fine. 30 sites, 1 billion. 40 sites, 1 trillion. 50 sites, and you're at 10 to the 15. You've blown past the memory of any computer on Earth. And this isn't a matter of waiting for better hardware, it's the structure of the problem. In our own work, tracking the interacting many-particle version, hardcore bosons hopping and interacting on the near-horizon lattice, the memory you need scales like the number of ways to arrange the particles among the sites, and on a laptop that crosses the practical limit, around 100,000 configurations, at a chain length of only about 19 or 20 sites. We measured exactly where that wall is. It's at L, roughly equals 20. That's shockingly small. 20 little sites and an ordinary computer is already defeated.
Now I have to push because a physicist co-author will. There are clever classical methods, tensor networks, matrix product states, DMRG, that go way past 20 sites for many problems. Why don't those save us here?
You're absolutely right that they exist, and they're spectacular, for the right problems. But they have an Achilles heel, and this problem walks straight into it. Those methods work by exploiting the fact that, in many physical states, entanglement is limited. It only follows the boundary of a region, what's called an area law. When entanglement is modest and local, matrix product states compress the description beautifully, and you can reach hundreds or thousands of sites. But scrambling, the exact phenomenon we care about, the black hole interior thermalizing information at the maximum rate, is defined by entanglement growing to fill the entire system. Volume law entanglement, not area law. Every part gets maximally tangled with every other part. And that is precisely the regime where tensor networks blow up. The resources they need grow exponentially again, and you're right back at the wall. The classical shortcut works everywhere except the one place we want to go.
So the very feature that makes the black hole interior interesting, maximal scrambling, is the feature that makes it classically unsimulable.
That's the poetry of it, and it's not a coincidence. The scrambling interior is hard for exactly the same reason it's interesting. It's using the full exponential vastness of Hilbert space, holding information in the global web of correlations that no efficient classical description can capture. And what's the one machine that natively lives in that exponential space, that stores information in exactly that web of correlations? A quantum computer. A quantum processor doesn't simulate 2 to the L amplitudes by storing 2 to the L numbers. It is a physical system with 2 to the L amplitudes. It scrambles because it's made of the same quantum stuff. So the interacting, scrambling horizon interior isn't just a nice application for a quantum computer. It's arguably the natural target. The place where a quantum processor isn't a convenience, but a necessity.
And that's the bridge to the hardware part of the project. You actually ran pieces of this on real quantum computers.
We did, and I want to describe it honestly, including where it's hard, because the honest version is more useful to you than a triumphant one. On the theory/simulation side, we designed the full circuit, a trotterized quantum walk, meaning you approximate the continuous time evolution by a sequence of small discrete gate steps, plus a measurement of the OTOC to watch scrambling. We worked out the resource cost. Each time step needs about 2 times L-1 2-qubit gates, and we drove the trotter approximation error down to under 2 times 10 to the -5 in simulation. We confirmed the OTOC grows over time, and, the physics payoff, it grows faster in the curved, near-horizon geometry than in flat space. Curvature accelerates scrambling. That's the kind of statement you can only make by building the interacting version.
And then onto actual chips.
And then onto actual chips, across multiple vendors, which is where you meet reality. On IBM's hardware, a processor called IBM Fez, we ran the quantum walk and got a median gate fidelity around 0.987, which is quite good, and we saw a clean contrast. The output probability at the relevant site was about 12 times larger in the curved geometry run than in the flat one. So the horizon signature survived on real, noisy hardware, a genuine result. We also ran on a Rigetti superconducting chip, which cost us about $32 of cloud time, and there, honestly, the contrast did not resolve at the circuit depth we could afford. The noise ate the signal. And we report that too. That's a real, if humbling, cross-vendor data point. The same circuit, one platform shows the effect cleanly, another washes it out at depth. That tells you something true about where the hardware is today. We don't hide the run that didn't work.
I really appreciate that you keep coming back to the failures and the caveats. It makes the successes believable.
It's the only way to do it. Look, the entire value of a reproduction project is trust. If you only ever report the runs that worked and quietly bury the ones that didn't, you've built a press release, not a piece of science. Everything we've talked about, the 1.8 factor we didn't correct, the sign inconsistency we flagged in someone else's equation, the Rigetti run that didn't resolve, the Floquet heating that limits everything. Those aren't embarrassments to minimize. They're the texture of real work. When you sit down with your co-author, leading with the honest caveats is what earns you the right to be believed about the wins.
Let's land the plane. Give me the whole arc in one breath, the thing I should be able to reconstruct on a whiteboard from memory.
Here's the whole thing in one breath. A black hole has a temperature discovered by Hawking, and that temperature is set entirely by the local steepness of geometry at the horizon. The surface gravity, nothing else. Unruh showed you don't need gravity for a horizon. Any medium where a flow overtakes the local signal speed will do, which legalizes building horizons in a lab. On a chain of atoms, the hopping amplitude plays the role of the local speed of light. So a position-dependent hopping is a curved spacetime. A hopping that passes through zero is a horizon. A hopping that changes sign is the interior, and the slope of that hopping ramp, divided by 4 pi, is the Hawking temperature. You build those exotic sign-changing hoppings by shaking the lattice, Floquet engineering, where the Jacobi Anger expansion tells you the effective hopping is renormalized by the zeroth Bessel function of the drive strength, which conveniently passes through zero and goes negative exactly when you need it to. That's the single particle story, and 3 papers carry it. Benamou's cold atom blueprint, Nixon's Floquet toolkit, and Xi's superconducting chip demonstration.
And then the second act, information.
And then the real prize, the second act, is information. Turn on interactions and the horizon scrambles, smears local information across the whole system at the maximum rate physics allows, saturating the Maldacena-Schenker-Stanford chaos bound in a scrambling time that grows only logarithmically with size. You measure that scrambling with out-of-time order correlators, or you certify it cleverly through teleportation, as Landsman's ion trap experiment did. Hayden and Preskill showed an old black hole spits information back out almost immediately, and the page curve, entropy rising then falling, is the signature that information is conserved after all. But that interacting, scrambling, information-returning regime lives in the full exponential vastness of Hilbert space, with volume law entanglement that defeats every classical method, including tensor networks, right around a chain of 20 sites. And the one machine built to live in that space is a quantum computer, which is why the endgame of this whole project is real quantum hardware, running the scrambling interior that no laptop can touch.
That's a genuinely beautiful arc. Geometry becomes hopping, shaking becomes control, interactions become scrambling, and scrambling becomes the reason you need the quantum computer in the first place.
And every rung of that ladder, in our project, has a number attached to it, a reproduced figure, a matched percentage, a real hardware run with its fidelity and its cost, and its honest caveat. That's what turns a beautiful story into a defensible one. When your co-author pushes on any single rung, you don't have to wave your hands. You can point to the result, the method, and the thing it doesn't yet do.
This was exactly the catch-up I needed. Thank you for taking it slowly and keeping it honest.
My pleasure, Nadia. Go have a great conversation with your co-author. And remember the one sentence, if you remember nothing else, the temperature of the black hole is the slope of the hopping ramp, over 4 pi. Everything else hangs off that.
The slope of the hopping ramp over 4 pi. Got it. That's the show. Thanks for listening, and we'll see you next time.